Hi, Nagus.
Hi, Peter. Thank you for inviting me to your podcast.
Yeah, welcome.
Great pleasure to have this conversation with you today. And I was looking forward to our chat today, and I'm very glad to be here. Thank you.
Yeah, I have also been looking very much forward because today we are going to talk about really the future and how materials might be able to save us in the future. Uh, because we're going to talk about future energy supplies using fusion. And I've been following the Iter project, but I've never dig deeper into it. So therefore, I'm very curious to learn more about that today. Um, but first, I would be very happy if you could introduce yourself, your name, your background, and how you became interested in materials.
That would be my pleasure. Yes. Peter, first of all, I have to introduce myself. Yes, my name is Narguess, my family name Nemati, and at the moment, I'm an assistant professor in the Department of Mechanical and Production Engineering at Aarhus University. My background is all material science. I'm a material scientist by training from bachelor, master, and PhD. Um, it was about 2016 that I was a fresh PhD graduate when I heard about fusion,
Mhm.
and I got very much interested in the idea of bringing the sun on Earth and producing energy
Mm.
imitating from sun. That was the very basic idea that I read about in an article, and then I thought, how cool! And what are the challenges? Why didn't we have it so far? And
Mhm.
then I understood that there are some major challenges about realization of fusion, and one of the big challenges is materials for fusion.
Mm.
Obviously,
Yeah.
from there, my journey with fusion started. As a postdoc, I went to South Korea after my PhD.
Mm.
And then in South Korea, I worked on harsh materials, materials for harsh condition actually. And then I expanded my expertise on design and
Mm.
manufacturing coatings and advanced materials which can resist harsh condition in service, similar to what materials for fusion need to
Mm.
resist. And then for 4 years, I have been working in two different laboratories in Yonsei University, one of the top universities in South Korea, on materials for harsh condition. Then I got closer to fusion community by my next role in Max Planck Institute for Plasma Physics in Germany, where the main focus of the whole research institute is realizing fusion through magnetic confinement approach. And I had been a researcher for 2 years in Max Planck Institute, specifically working on materials of the divertor, which I will explain shortly. What is
Mm.
it? And my next journey was Denmark and Aarhus University, another postdoc, and then now my new role as an assistant professor since August 2022.
Mm.
But that was a short introduction of myself and how I am related to material science. Um, about the ITER project you mentioned, your
Yes.
actually ITER stands for International Thermonuclear Energy Reactor, and
Mhm.
it consists of 8 major entities. European Union is one of the entities which has 55% of the share of this big project
Mm.
from the funding and from later the benefit of that. Then there is India, Russia, South Korea, Japan, and it was USA before that
Mm.
there were discussions if they want to continue with ITER or they want to pull back and start their own program or focus on their own national program. Iter organization is located in South France, Cadarache. This is the location that the Iter organization is being built up. And it has been fantastic and incredible development over the past few years in the construction of the site and the reactor itself. And the main approach for the Iter is that magnetic confinement, because there are different approaches for fusion, and one of them is inertial confinement, and the other one is magnetic confinement. What do we mean by confinement is that in order to realize the fusion reaction happen and the chain of reaction be sustainable, we need to hold the plasma, the very hot plasma, for sufficiently long time, where deuterium and tritium reactions can happen, and then the chain of reaction can go on, and as a result, the vast amount of energy is released as a result of that reaction, and then that energy can be harnessed, and then it can heat the water, boil the water, and then connected to the grid, and then bring electricity. So the plasma need to be heated about millions of kelvins, like what is happening in the core of the sun, really. And that was not a problem, since it happened locally when now in different tokamaks around the world you measure the temperature. Raising the temperature that high is not anymore the problem and issue. But confining the plasma for sufficiently long time without getting locally cold, or to avoid the instabilities of the plasma, or to control the alpha particle instabilities and heatings, they are the major issues, along with some other issues that we still don't have that yield that is acceptable for fusion. By that, I mean the input of the energy for the fusion to happen is still higher or slightly equal to the output of the energy that we can get from the reactor. In order to make the output higher and then make the yield of the energy production higher, we need to work on the problems that associate with the fusion at the moment. So this is a little bit of about the Iter project and what is the aim of it. It's going to demonstrate the whole world that by using deuterium and tritium, we can achieve a sustainable energy production. And then Iter is not going to connect to grid, is not going to bring electricity, is a demonstration of possibility of harnessing energy from deuterium and tritium, which then connect us to hydrogen, and how the role of hydrogen in the future energy agenda of the world is. Shall I continue, or do you have any question?
Yes. If we start with the raw materials, you said deuterium and tritium, but where do they come from, these materials? Do you harvest them from seawater, or where is it? Where is it found, and how is it separated?
Okay, that's a very good question. Actually, deuterium and tritium as the two major isotopes of hydrogen. Deuterium is abundant, is easy to extract from the seawater. In every cubic meter of the seawater, we have 33 grams of deuterium available, or in other words, 1 per 6,700 hydrogen atoms in the seawater is deuterium. So deuterium is easy to get. But tritium, it needs a reaction between lithium and neutron particles, or boron and neutron particles. So it's a low energy fission reaction between neutron, the neutral neutron is, and then lithium-6 that can lead to production of tritium. And that is foreseen in the Iter program, in any other confinement, magnetic confinement scenario. How? They put a breathing blanket within the walls of the tokamak, When the deuterium and tritium react,
Mhm.
the result of that reaction, the production, is helium and neutron. These fast neutrons came out of the plasma, and then they run away, or they exit the plasma, and then they hit the walls. And then from the walls, they are transferred to the breathing blanket, which consists of lithium. In the reaction that happens between lithium and these neutrons, tritium produced is being circulated back to the reaction, and then makes another reaction with deuterium, and then neutron, helium, again lithium. And this is how the sustainability of the reaction is designed.
Aha. So you have a sacrificial blanket on the inside of the tokamak.
We have that lithium, we call it breathing blanket, which is going, its major responsibility or role is to provide a special place that lithium can react with the neutron and produce the tritium, and then tritium goes back and react with deuterium.
Yeah.
Now in the world, it's interesting to know that only 2 tokamaks, one in Princeton and the other one in the European tokamak jet in UK, are using deuterium tritium as the major fuel. And we have been learning a lot from the reaction of the deuterium and tritium in the jet reactor. And jet became 50 years old a couple of months ago, and people celebrated that 50 years of learning from jet deuterium reaction.
And how do you feed it into the system? You also, so now you have the tritium, it is feeded from the blanket, but how do you feed deuterium inside the system?
They are like a gas, and then the gas is going to blow inside the vacuum. There is a major vacuum vessel, and then these gases are being blown into in a controlled manner, and then the system is being heated, and then this reaction happens when the heat is sufficiently high enough.
I have seen other processes where they use liquid lead for as a production tank to produce tritium. Is that a process you are aware of?
Actually, that one, because of the environmental concerns, have not been developed or have not been a major interest of the big entities of fusion, because of the environmental concerns of the lead. But yes, that's also a possibility of producing that.
Yeah, and do you know how it works?
I am not sure about that. I haven't informed myself about that.
Okay. So when we look into the tank or the tokamak, what are the walls made of? Because when you have something that is 1,000,000 degrees, you must have some quite severe radiation. So how do you build it? What kind of materials are used in such a machine?
It has a long story. The first wall of the tokamak has gone through different scenarios. In the past, they used carbon fibers, but the volatile hydrocarbon side productions were major problem, and then they decided that carbon is not allowed anymore, and then become the major candidate for the first wall. And so far, it has not been proven wrong that tungsten is the best material to be used as the first wall. So tungsten is the main candidate for Iter, for West, which is the tokamak in France again, for any tokamak around the world. People are using tungsten, and I was working on the tungsten divertor material when I was in Max Planck Institute. For example, I can tell you what I was working on was the recrystallization regime and grain growth regime of tungsten in the presence of these high heat fluxes, and how we can control the grain growth, or how the recrystallization in the cyclic heat flux loading can be different from the steady state heating, which is the normal situation. And we have learned from tungsten steady state heating how we can control the grain growth and recrystallization of the cyclic high heat flux loading. So this is one of the issues that we have to know and we have to learn, because we never had the chance in any other facility that exposed tungsten for such a high heat flux cyclic load to learn tungsten what would be the concerns about the degradation of the material. And yeah, tungsten is now the only candidate for the first one to withstand extreme condition.
But it must become pretty hot. So if you don't cool it, then it would melt, even though tungsten does not melt. What is it? 3,400 degrees, the melting point.
It is about that. But as you said, because we have this vacuum in the whole vessel, the only way for transferring the heat is radiation, and the heat that the tungsten wall, the maximum heat that the tungsten wall reaches in different locations is different, but it's about 2,000 degree maximum from the heat of the plasma that by radiation is transferred to the first wall. And I have to now talk about the superconducting magnets that provide this environment to hold the plasma. And we have two different cooling issues for the tokamak. First of all, we have to cool down the superconducting that produce that magnet, that magnetic field. As you know, we don't have the room temperature superconductors in a scale.
Not yet.
Not yet, but that would be one Nobel Prize reserved for that, I would assume.
Yes.
If we have that, right, you agree with me? If we have that superconducting material for room temperature, then the fusion yield would definitely rapidly go higher, and it gets much closer to industrialized fusion. That's one of the major issues. And the second cooling issue is that we have to cool down the wall. So we have to cool down the wall from the behind and then we have such a gradient of temperature. At any moment we look at any block of the first wall, they can be as high as 2,000 degree or as low as about 400 degrees centigrade, because we put some coolant around it, and then liquid nitrogen, for example, is one, and then we cool it down to avoid the grain growth or any other issues that can relate to the high temperature, constant high temperature.
These is a blocks of tungsten. How do they look, and is it pure tungsten or is it an alloy, and how are they manufactured? I'm very curious.
That's a very good question. Actually, the tungsten itself is not a pure tungsten. It has some trace alloying elements. And the tungsten producers for these tokamaks are two major companies. One of them is in China, the other one is in Japan. And I have the companies, but if you are interested, we can talk about it. So they produce the fusion grade tungsten, and the tracing elements are kind of secret and the black box. We don't know about it, but we know that there are some controlling elements that they control the grain growth and the recrystallization regime. So they are tungstens for the fusion. They are not any pure or normal tungsten. This is first of all.
Yeah.
And then the blocks, they each monoblock consists of a tungsten, like a cube of tungsten, and then there is a hole in the cube that one pipe goes through that hole, and then this is where you actually you put the cold water for the diversion part, and then you try to cool down the tungsten part by circulating the cold water inside it. So and these parts are manufactured by different production lines. One of them, for example, is in Inia in Italy. They produce these tungsten monoblocks with the pipe, and between the pipe and the tungsten block there is a copper layer that helps this heat transfer and heat conduction. So this is like tungsten, copper, and this pipe, and then the pipe is responsible for circulating the cool water and to cool down the diverter parts. So this is how they manufacture it, and how the tungsten itself, they are like slabs, and then some of them go through the rolling, cold rolling, and some of them go through the hot rolling, and depending on which part of the wall we are talking about, they use different processes for tungsten manufacturing.
Okay. I thought it would be made with powder metal and hot isostatic pressing to make these channels inside.
That is also in a limited way they are trying it, because they think that would yield higher or better properties. That is also being tested. That is also being tested.
Yeah.
Even 3D printing and additive manufacturing of and monoblocks on copper substrates is also being applied, because they think that by additive manufacturing they have a better control, and they are making a porous structure of tungsten with different controlled pore size and geometry on the copper, and then they think that this is also another scenario that they could help with control of the heat transfer.
Yeah. So these you call them monoblocks?
Yes.
How are they assembled? Are they just mechanically attached to each other, or are they welded, or how do you seal and secure that you have a vacuum?
Oh, welding is not an option. So this is because of the flaws that you are aware. Welding always come with a little bit of chance in the best scenario of the flaws in the welding part. So welding is not an option. So they are mechanically attached for now.
So when they are mechanical attached, there must be some space in between. How much happens with thermal expansion when you heat it up to 2000 degrees? It must expand a lot.
I think tungsten, because like I said, they cool it down constantly, and from there you control this expansion in a way that it doesn't yield in breaking the seals, because that cooling rate is precisely calculated in order to avoid such big expansions.
Okay. But now when it's only mechanical and you have a ultra high vacuum, how do you secure that you have the vacuum? Is there, I'm guessing you said this is the first wall, so there must be another wall behind it. What is that?
Actually, I am not aware of the latest technology about the vacuum control of this. I was much more into material part of it, but I am also curious to learn about how they control the vacuum and how they keep it from behind the first wall, because like you said, first wall is always there is susceptible to have that expansion and then losing the vacuum. But I'm also curious to learn. I have not informed myself about the latest technology of the vacuum control.
But then there's a second wall behind the tungsten wall. What is that made of?
This is that breathing blanket, basically, which is made of lithium. And then when the neutrons finally pass through the wall and then they have this incident with that breathing blanket, then the scenario of the tritium breathing is happening. And then you have another layer that finally the neutrons, quite a slow down neutrons, will be heating that wall, and then their heat is transferred to that wall, and then that heat would finally boil the water and then continuing to produce the energy.
Okay, so it's still an old-fashioned steam boiler under pressure
Exactly.
with a standard gas turbine.
Exactly. The only thing that is different is that source of heating is different. Otherwise, we need to boil the water and then go to the grid.
Yeah. So when you have all these walls, there must be some you could call thermal delay. So when you start the reaction until you have heat going all the way through, it could take hours. Or how fast does it react?
Actually, in order to have to produce the energy is pretty fast. As soon as you have the first chain of reactions, deuterium, tritium, occurring, you technically have the heat and neutron produced. But I mean, when you have the neutrons as a product of that reaction, it means that when the neutrons very fast hit the wall, they release the heat to the wall, and then you have the heat available. But in order to be sustainable, you need to confine the plasma for a certain time. And that's one of the major issues with realization of the fusion as a major source of energy, because yet we are not able to stabilize and confine the plasma long enough for a sustainable chain of reactions. And instabilities of the plasma and heating alpha particles, and also along with problems with the materials for the first wall, they are all together the issues that should be overcome to have that energy realization as a sustainable source of energy.
I heard some years ago that there are also stainless steel inside the system. It was almost a standard 316L, but there was a specification that it should be ultra low cobalt version. Because when you have cobalt into such a system, you can change the cobalt configuration to cobalt 60, which is long-term radioactive. And the target was that when you turn off this machine, you should be able to walk in when it's cooled down and not be hit by radiation. So therefore, they have defined special grades for fusion reaction. Is that something you could elaborate a little more on?
There was, first of all, the steel that you are mentioning is used in a structural part of the reactor, not in the main part of inside the tokamak. But the structural parts are all, we have no other option than steel, of course. But one grade that is especially designed, as you mentioned truly, about the concerns that could be about the steel production or steel elements. One grade is Euroferrous steel, that is low cobalt and then is high in tungsten, and then this irradiation is a lot controlled by the elements that are incorporated in that kind of a steel. That's how much I can recall now from the steel area.
Yeah. So is tungsten used because it's a good blocker of radiation, like you use
Absolutely.
lead?
Absolutely.
Mm-hmm. So how does the neutron pass the inner wall of tungsten and go through and heat? Is it because the radiation is so heavily that it just runs through and heats up the water?
Actually, neutrons that are produced from this reaction have a very high energy, and they are the fastest neutron that can be produced. So because they are very fast and high energy, they easily pass through any material. And then during their passing through by different incidents, they lose energy. And then until they reach that material, that blanket, and then when they pass through that, they release all the heat finally. I mean, you have to slow them down in a way that in a final destination, they can really release the energy, and then you can harness that energy. So they are fast enough when they are produced first that they can go through the tungsten wall.
Yeah. Inside the chamber, you must also have some nozzles where you can suck out the vacuum, where you can let in the new gases. What are these nozzles made of?
That's a good question. I am not sure. I'm not sure. I have to look up that one.
Yeah. Because that must also be some quite stressed materials.
Yeah, definitely. Yes.
Yeah. Then when you make the fusion of the deuterium and the tritium, your product in my head is helium and a neutron. Is it helium or is it alpha and some electrons in a plasma?
Electrons. This is alpha and electrons. Yes. And then we have these runaway electrons, which is another problem that can cool down the plasma, which is not wanted. So this is alpha particles and electrons, basically.
And they are then caught in the plasma.
Yes, they are.
So how do you get them out when you want to have a running production?
You have an exhaust. So this divertor is all about the exhaust, and then you exhaust the particles and the energy from the exhaust part of the machine. So it exhausts them, and then this part is totally from tungsten monoblocks, and the whole module is called divertor. And then the exhaust goes through that divertor, and then you exhaust this through this.
How many kilos of tungsten monoblocks are in a test facility like the Iter?
Wow, that's hard to answer, but I would say that I had some numbers in mind about how big is this to build. Iter is the biggest vacuum chamber in the world that is gonna be built up. Yeah. And then there is like a solenoid in the center of this reactor, and it is toroidal shape for confinement of the plasma. There are different modules that they are being built individually, and then finally they are going to be attached that they provide this toroidal shape inside the wall. If you look at the tokamak from inside or the Iter schematic shapes available, you can see that each individual part of the whole reactor looks like one donut shape, and then all together, when they are attached and assembled, they are going to keep the plasma in a donut shape. So yeah, I forgot your question. How big is it? How big is it? Yeah.
Yeah, and how many tons of tungsten are inserted? It must be pretty heavy.
Yeah, this is massive. I don't have numbers, but it could be very massive.
Yeah. So when do you expect that fusion will be a running energy supply for our future society?
There was always a joke that fusion is 30 years ahead, always, but
Yeah.
now not anymore. I believe by advancement in the science and technology, especially the physics of the tokamak is very much advanced today. And now specialists are touching the technological shortcomings and issues about fusion realization, which is now the role of engineers to solve it. There are so many different startups around the world, mostly in America and Germany, that have promises to realize the fusion by 2030. Not realizing, but also commercializing. And there are different scenarios of fusion energy realization. As an example, some startups in Germany, which I don't name them, they have promises for working on astralator scenario, and they think that that is the most promising way of realization of fusion energy other than tokamak. And there are some other startups in America that they work on inertial fusion confinement, that they work on laser-based fusion energy. What they do that basically they think they can have a fuel in a very small compact chamber, as small as one sphere of a fuel, and then they focus a very high intensity, high energy laser beam to heat up and explode that fuel plate, and then they explode as the energy is released. So this is one scenario, and NIF in America reported that they had some good yield for the energy production compared to the energy input. And then Germany and America, again, at the same time, they are working on magnetic confinement fusion. And they have promises for 2030 to realize it. And Iter itself is going to be finished by 2030. So I'm very excited about these 5 years ahead of us. And I think that they are not far from reality because, like I said, now a very good amount of knowledge and technology is being accumulated over the years that they can converge and make it happen.
So an industrialized machine like the Iter, are there plans for building one that should be connected to the grid?
After Iter, there will be one called Demo, which is also a demonstration tokamak and is bigger than Iter. So the scale of the Iter is like 1/3 of Demo, and then Demo is going to be the next. And then after Demo, if all of them are success, then there will be these commercialized tokamaks that these entities of the Iter are going to build them up and sell them to the countries who are interested to the technology and science of it. So we are talking about 40 years from now to have that energy in our grid provided by fusion. But then we have to remember that that's eternal clean energy, meaning that we get rid of carbon footprint, we get rid of the expenses that now we are paying for providing gas and oil from certain countries. And it means that even our ambitious goals to explore the space will happen, because then we have a motor that can never stop, and then we can go as far as we want, as fast as we want, with that eternal energy, and we can discover the other planets, interstellar spaces, which is not possible now because we don't have that much fuel to continue between the interstellar spaces. So basically it's going to change the world, and I am very excited to survive and be alive and see such advancements to happen.
Yeah. So we need to keep alive for 40 years more.
Yeah, we need to survive only 30, 40 years, and then we see a very different world, and maybe the whole fundamental secrets of this creation would then be decoded, and then we understand more about where do we come from and where are we going after the death.
Yeah. Wow. It's we end on a high note.
Yeah.
Yeah. I am really looking forward to it, and I would love to learn even more. So if you have more information, or if people are curious, do you have interest in getting questions on it?
Definitely. I can even elaborate more on the technical issues related to fusion material and tungsten and divertor, which is what I have been working on, and I know better about that compared to other related problems about fusion. That would be very much welcome if I get any question, and I am always here and interested to answer. But what I want to say at the end of this conversation is that we have a fusion community in Denmark. I am a board member of a Dan Fusion, and Dan Fusion is basically an entity of Eurofusion. And Eurofusion is a big consortium that connects different European laboratories and different European institutes who work on fusion together. And then this converge of science and technology happens within Eurofusion. And Dan Fusion is now part of the Eurofusion, and we are representing Denmark. So Dan Fusion consists of DTU, SDU, Aarhus University, and Aalborg University. We have annual meetings, we have regular meetings for the board members. We share the news from the Eurofusion, we share the funding opportunities from Eurofusion, master projects, PhD projects related to remote handling and controlling because of the irradiation issues while the tokamak is working and on the service. You cannot have human working with it, so you should have this remote controlling, and this is one of the projects that Aarhus University is contributing for Iter and Eurofusion. There are so many exciting things going on from Denmark side that I would be interested to talk about them. And like I said, I became a board member of the Dan Fusion, and I have this honor and pleasure to serve there. And we are looking forward to have that contribution with Eurofusion more meaningful and more deep.
Yeah. But this also means that if you are a student and you thought that the only way to be a part of such a project would be working at CERN or working at Iter, then there are possibilities to work on this high-level project from Denmark.
Definitely, we can connect them, and we are actually doing that with our students who are interested. I have 2 master students who are working on fusion material simulation of the grain growth and structure of the grains of tungsten with phase field model and approving by experiment actually. So if students are interested to work on fusion from Denmark, there is possibilities to connect them to these world-class institutions and laboratories, and even they can get fund from Dan Fusion for short visits, summer schools, attending different workshops for fusion in Europe and even outside of Europe. So I highly encourage the students in different universities in Denmark to inform themselves from the Dan Fusion website, which is danfusion.dk, and they can always contact us, and we are more than happy to guide them to do what they are interested to do about fusion.
Fantastic. What a way to end the podcast. There is hope that you can develop the real hardcore future from a local Danish university.
there is a lot of hope that we can have a very big and meaningful contribution to that mission. And we are here to promote it as much as possible for young, talented people who think they can have this mission defined for themselves to contribute in eliminating the carbon footprints from the planet. And fusion is a promising way for that. And from Denmark, even though Denmark traditionally is known for using the renewable energy systems like wind energy. But now I'm very happy to announce that Dan Fusion is doing great to promoting contribution of Denmark for fusion energy.
Thank you. I really enjoyed the conversation.
Me too, Peter. Thank you for having me. It was a pleasure to talk to you again. And I hope that people liked the story we told about fusion.
I am sure. Talk to you soon.
Talk to you soon. Thank you. Bye-bye.